This is Programming Chapter 6, Part 3. We're going to be looking at how to search through arrays, specifically sorted arrays. A common operation is to look for a name in a list, but we're going to just start by using numbers for ease. This is because using strings is a little bit more difficult, and it's different for each language, and we want to try to keep all the languages the same for now. And an obvious way to do this is to start at the beginning of the list and check each item until we get to the end. This has an efficiency of order n, and we did this in exercise 5.3, doing the index of string function, and it's called the linear search. Exercise 6.5, you're going to be using your code from exercise 6.4. You're going to get a number from the user, and we're going to search for that number. You're going to write a function to search for this number, and it should return the index of the number. And once the number to search for is less than the current element, we can terminate the search since the list is ordered. For example, if we were to search for 27, which would be here, we can stop after 28 because all the numbers are going to be bigger than 27 after that. If we don't find a number, we return -1 for the index, and this is a common return value because we don't ever have an index of -1. And your output should say whether the number was found or not, and if you find it, you should print out the index number. And part of your output should also include printing the random list at the beginning. This way we can verify the search for correctness. And the efficiency is order n. And you might think that that's efficient. However, there are algorithms that can search with an efficiency of O log n. And remember, this is log 2. And this is called the binary search algorithm. For a list size of 100, the number of comparisons is 100 versus 7. Log base 2 of 128 is 7, so 100 is slightly less than 7, but we round up. So 100 divided by 7, we have a multiple of 14 times slower. For a list size of 10,000, we have 10,000 versus 14. This is a multiple of over 700 times slower. You might not think that you would ever have arrays this big, but if you're writing a game and you're rendering polygons for collision detection, you would easily have over 10,000 polygons. So, how do we implement a binary search? And it's a matter of using the high-low game strategy. And what this does is we divide the list in half every time. And by dividing it in half every time, the list gets small very quick. So to do this, we need to have a bottom and a top, and in our case, a left and a right of the list, but we still call it bottom and top. And we'll demonstrate with a search for the number 48. So the first step, we need to set the bottom and top to the first element and the last element. And we need to check the mid. The mid is simply the bottom plus the top and divided by 2. So 15 divided by 2 is 7.5, and we truncate that. So it's just 7. We check 48 against this mid value. It's bigger. So we go up to the next one, and this is our new bottom. Our new bottom. Now we just go back to the beginning of the loop. We have 8 plus 15 divided by 2. That's 11.5. But again, we truncate. So this is element 11. 48 is bigger than 37. So this is our new bottom, 12. 12 plus 15 is 27, divided by 2 is 13.5. Again, truncated to 13. This is element 13. It matches, so we return 13. So we terminate when we find the correct value, but there's another way to terminate, and that's when the bottom index is greater than the top index. So the bottom index is greater than the top index. It never happened in this case. So let's demonstrate by searching for -7, and it's not in the list. So again, our first value is 7, and -7 is smaller, so this is our new top. Our next index is 3, and we have -3 is bigger. So this is our new top. That index is 2. And our new mid index is 1. However, 7 is bigger than this. So this becomes our new bottom. Notice that all the values are the same. We do one last check. We check against -6. -7 is smaller, so we have a new top. And remember, it's 1 less than our mid value. And now the bottom is greater than the top, and we can terminate the search and return -1. Your exercise is to implement this binary search. And what you'd like to do is add a variable to count the number of comparisons doing this search. You still want to do the linear search and count the number of searches in that one as well. And just to recap, when we have a new top, it's the mid -1. If we have a new bottom, we do the mid +1. And now that we've worked with arrays for a bit, we want to see how it's implemented in memory. When you declare individual variables, they can be placed in any order and not necessarily the order that you've declared them. And they might not even be in a contiguous block. For example, we declare A, B, and C, and we see that this is A, this is B, this is C. So this is allocated in reverse order, and it's not contiguous. There's some extra bytes in between. And in case you're wondering what these extra bytes are, they're for debug mode. It checks for memory stomps. And you don't have to worry about this now for now. When you make a release mode version of your program, these won't be there. And just to show you, these are the actual addresses. You can see that A has the largest address and C has the lowest address. Okay, so let's look at an array. This is an array of chars, which you've seen from the previous exercise. And you can see the ASCII code here. So it's showing you that it's contiguous. What is contiguous bias? To access any character, we're using CString with index. And the math to calculate this is the address of CString plus the index. So if we're looking at CString 1, that's this one. So the address of this plus 1 will give us the H. And because we're using the address of CString 1, to access the first element, we don't add anything. We add 0. And that's why we always have 0 as our first index. So let's look at an array of ints. They're all contiguous. 10, 7, negative 1, 10, 7, negative 1. When we allocate an array that has elements larger than a byte, accessing them is not much more difficult. For example, an int array has element size of 4 bytes. And we can calculate the address of ARR plus the index times 4. You think this might be slow, however, this is actually very quick for a computer. And multiplying by any power of 2 is extremely easy. And that's why we have native data types that have sizes that are a power of 2. I'll go over that in just a second. Let's take a look at the example of multiplying by 4. This 3, that's 3 times 4 gives us this. 5, that's this times 4 gives us this. And you should notice a pattern. All we're doing is adding 2 zeros to the end of the original number that we're multiplying by 4 by. And there's a special operation on the computer that does this. It's called shift left. And we shift left twice. And we pad it with zeros at the end. And this is akin to us multiplying by powers of 10 because we normally work in decimal. We don't actually do any arithmetic. We just add a 0 to the end. So if we're multiplying by 1,000, that's 3 zeros that we add to the end. So 5 times 1,000 is just 5 with 3 zeros. Now, we have bytes, and they have a size of 1. We have shorts, they have a size of 2. We have ints, size 4. We have longs, and that's size 8. This is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. So we're doing powers of 2. Any powers of 2, here we don't need to shift. Here we would shift by 1, here we'd shift by 2, here we'd shift by 3. So, in conclusion, arrays are very efficient for accessing any element. And that completes Chapter 6.